The Royal Swedish Academy of Sciences has today decided to award the 2024 Nobel Prize in Chemistry with one half to David Baker, University of Washington, USA, for computational protein design, and the other half jointly to Demis Hassabis and John Jumper, Google DeepMind, United Kingdom, for protein structure prediction.
地球上所有的生命都是由细胞组成的，而细胞的功能，包括通常被认为不是生命的病毒的功能，都是由蛋白质执行的。蛋白质是由20种氨基酸通过肽键连接形成不同长度的多肽。不同的生物的基因组编码的蛋白质数量差异很大，大肠杆菌只有4000多个蛋白质，而人有2万多个，加上拼接变异体，数量就很大了。人类蛋白质只有一半会自发折叠为独特的3维结构，而另一半则不会形成固定的结构。最新的研究表明，不会折叠的蛋白质驱动液液相分离过程，形成无膜的细胞器，但这不是本视频的重点。本视频只讨论会形成特定3维结构的蛋白质。蛋白质从没有固定结构的多肽自发形成特定的3维结构，就叫蛋白质折叠。蛋白质的结构是功能的基础，比如负责细胞内合成蛋白质的核糖体，就是一个有几百个多肽和 RNA 形成的巨大复合体。还有病毒的外壳也是由蛋白质自发组装形成。蛋白质的什么性质决定它的3维结构？这个问题就是蛋白质折叠问题。这个问题早在上世纪60年代就由科学家安佛生用一个只需要半天就能完成的试验解决了。这个实验结果表明，蛋白质如此复杂多样的3维结构是由它的氨基酸系列决定的。这是蛋白质折叠问题最重要的里程碑，所以安佛生很快在1972年就获得诺贝尔奖。蛋白质折叠通常在几微秒就完成，所以科学家对它的机制仍然不清楚，被公认为对人类智力的最大挑战之一。以前要知道一个蛋白质的3维结构，就只有用 X 射线衍射、核磁共振或者冷冻电镜测定，但这既费时又极端昂贵，而且需要多年的训练。过去科学家一直努力用计算机方法从蛋白质的系列预测它的3维结构，但准确性极低。不过，辛顿教授在加拿大顶住半个多世纪主流科学界讽刺打击，终于让神经网络人工智能突然爆发。这一人类历史上最大的突破，不仅有了让任何人类围棋棋手毫无胜算的 AlphaGo， 也有了 ChatGPT、Sora、Suno 等，而且自然而然也让 Google 公司在2021发展出了能准确预测蛋白质3维结构的 AlphaFold 2，以及几个星期前公开的能预测蛋白质核酸、蛋白质小分子复合体的 AlphaFold 3。后面就是他们的简单介绍。
Of their amino acids. From the central dogma, we know that DNA is transcribed into RNA and then translated into an amino acid sequence, which contains all the necessary information to reliably fold into a three-dimensional protein. Researchers have successfully determined protein structure experimentally, using methods such as X-ray crystallography, nuclear magnetic resonance spectroscopy, and cryo-electron microscopy. But these methods are time-consuming and expensive, meaning useful 3D protein structure models. Here is a simplified diagram of AlphaFold 2's architecture. We'll break it down into 3 sections and start here. When an input sequence of residues or amino acids is entered, AlphaFold compares it to several databases of protein sequences to extract similar sequences from various organisms and tissues to generate a multiple sequence alignment, or MSA, and an initial MSA representation. It also pairs the input sequence and searches databases for templates of similar sequence proteins with experimentally determined structures. This is then used to create an initial pair representation of the input sequence, representing the relationship between every pair of residues within the target protein. From here, we can move on to section 2, the evoformer. The evoformer is a neural network unique to AlphaFold. It consists of 2 towers that can communicate information to each other. For the MSA representation, the neural network prioritizes looking for row-wise relationships between residue pairs in the input sequence, before considering column-wise information that evaluates the importance of each residue in context of the other sequences. The pair representation tower evaluates the relationships between every 2 residues, which can be thought of as nodes, to refine the proximities, or edges, between the 2. It achieves this by triangulating the relationship of each node in a pair relative to a third node. The goal of this process is to help the network satisfy the triangle inequality theorem, where the sum of 2 edges on a triangle must be equal to or greater than the third. So how and where do the 2 towers communicate? Before the pair representation calculates the triangulations on each edge, it considers the updated MSA residue relationships and updates each edge accordingly. The results of the pair representation data is then used in the MSA's row-wise weighting of pair relationships in the input sequence prior to its next round of row and column-wise evaluations. These individual and cross-communicated calculations happened 48 times in the evoformer before creating the refined models of the initial MSA and pair representations. The final section involves another neural network called the structure module. It takes the refined models and performs rotations and translations on each amino acid, revealing an initial guess of the 3D protein structure. It also applies physical and chemical constraints dictated by atomic bonds, angles, and torsional angles. The refined models, as well as the output of the structure module, is iterated back through the evoformer and structure module process 3 more times, for a total of 4 cycles, before it arrives at the final result, predicted 3D atomic coordinates for the protein's 3D structure. It's important to
总而言之，现在的人工智能不需要懂得蛋白质折叠的机理，也能读懂蛋白质折叠的语言，因此能准确预测蛋白质的三维结构。反而，人类依然不懂蛋白质的折叠语言。这一折叠过程只是蛋白质折叠的计算机模拟。现在已经越来越清楚，蛋白质折叠和功能之所以对人类仍然是巨大的谜，是因为我们根本不能理解最神秘的分子水